This is a pretty easy slide for me to make because it's virtually identical to a slide that you've already seen before. I just copied it over and changed a couple words. Instead of position time graph shapes, we've now got velocity time graph shapes, but you notice that the shapes that we've drawn here are exactly the same as they were for the position time graphs. We just changed the y-axis. Remember that the manipulated variable always goes on the x-axis, so that would be time. Responding goes on the y-axis, so that would be velocity. And remember that just like in position time graph, the title is always going to be the y-axis or responding variable versus the x-axis or the manipulated variable. If you were to see data for these graphs in a table, it would be time in the first column and velocity in the second column. All right. So what does each of these graphs, or the shapes of each of these graphs, represent? If I had a position time graph like the first one, where it was a straight line but sloping upwards, it would mean constant velocity. That's not what it means here. Can you tell me why first it doesn't mean constant velocity? We can explain in a minute what it does mean, but tell me why it doesn't mean the same thing as the position time graph. Yep. Yeah. Yeah, look, the velocity is something right here. The velocity is something a lot bigger right here. So it can't be a constant velocity if the velocity is going up, the velocity is increasing. What do you think that means if the velocity is increasing? Yeah? Yeah, it's an acceleration. It's specifically a constant acceleration. We know that because it's a straight line. Actually, I'm going to say it's a constant positive acceleration, right? Because it's increasing, means it's speeding up, right? I mean, if you wrote down that it was speeding up at a constant rate, that would work as well. But we do want to distinguish that between a constant negative velocity, because a negative velocity would be slowing down. If I had a position time graph, the second one would mean that the object has stopped. Yeah, the position wouldn't be changing. What's not changing in this one, Kelly? The velocity is not changing. So if the velocity is not changing, then what would you say about this? It's a constant velocity. Now, in this case, it is a constant positive velocity because it's above the x-axis, but you could conceivably see one like this, where that's still a constant velocity, right? But it would be a constant negative velocity because it's below the x-axis. What about the third one? Negative constant velocity? No, not negative constant velocity, but you're close. Negative constant acceleration, right? So the acceleration is uniform, but you're slowing down. What does that mean, constant acceleration here? Like the velocity is changing. How can the acceleration be constant when the velocity is changing? It's kind of like, we've gone through this analogy a little bit before. When you put your foot on the gas pedal, okay, you accelerate, you speed up. If you keep your foot on the gas pedal in roughly the same position, you keep speeding up at the same rate. Now, if you put your foot further down on the gas pedal, not only do you speed up, but you speed up quicker. Okay, that's not what we have going on here. Okay, what we have going on here and here is that constant acceleration where you're speeding up, but the rate at which you speed up is constant. Moving to the next one, if this was position time graph, it would mean acceleration, right? If it's velocity time graph, it means acceleration. This time, it's specifically a non-constant or non-uniform acceleration. In other words, it's an increasing acceleration. If we were to use our analogy again of putting your foot on the gas pedal, this time it would be put your foot down on the gas pedal, but gradually put your foot further and further and further and further down. So not only are you speeding up, listen carefully, I don't know what to say. Not only are you speeding up, but the rate at which you speed up increases. So not only is your velocity increases, but the rate at which your velocity increases. Does that make sense? your velocity is increasing in graph 1 and in graph 4, but here it's increasing at a constant rate. Here it's increasing quicker and quicker and quicker. Yeah. No, that's a good question. No, the question was would the unit we'd use to represent this line be meters per second cubed? No, it'd still be meters per second squared because it's still acceleration. It's just that the acceleration here would be a different value than the acceleration here and here. How do you think you'd find, by the way, the acceleration at this one moment in time? Tangent line, right? And then find the slope of that tangent line. We'll deal with that in a little while. What's the last one? Velocity versus time, but it's curving, decreasing acceleration. So it means it's slowing down. No, not at all. Look, the velocity is increasing for the whole trip here, right? Okay, listen carefully to this one. Velocity is increasing, right? But the rate at which your velocity increases decreases. Your velocity is increasing, but the rate decreases. So that's like putting your foot on the gas pedal at the floor. You're accelerating really, really quickly, but then you're like, I'm going to go a little too quick, so you ease off the gas pedal. You'd still speed up, but you're not speeding up as quickly as you were before when you had your foot to the floor on the gas pedal. So this would be a decreasing acceleration. Still an acceleration, it's still speeding up, but the rate at which you speed up is decreasing. Well, just like with position time graphs, we can identify shapes. We can also identify some graph interpretation, reading numbers off the graph, doing some calculations with the graph, getting information, gleaning information from the graph. What can we get from velocity time graphs as opposed to position time graphs? Well, let's draw a little sketch of a velocity time graph. Let's say we've got something like this. How do you think you're going to find the instantaneous velocity on a velocity time graph? The velocity at a specific moment in time. Nope. Not the slope. Going up and over. You want to find the velocity right here, it's up and over. Look, if you wanted to find the position on a position time graph, it was up and over. Velocity on a velocity time graph, it's up and over. Power on a power time graph, it's up and over. Energy on an energy time graph, it's up and over. If you want to find whatever appears on the y-axis, you're going to go up and over. Finding the change in velocity on a velocity time graph. As you find the change in position on the position time graph. Up and over, subtract the 2, right? That's what we're going to do here. Up and over times 2, and then subtract the 2. In other words, it's going to be VF minus VI. This is up and over. This is up and over. Subtract the 2 of them. Acceleration on a velocity time graph. Yeah, that would be the slope. And the slope is delta y over delta x, right? But we could also find the acceleration on a velocity time graph by saying delta v over delta t. The slope, by the way, only works if it's a straight line, right? And, oh, this is a tough one right here, actually. This is one you're probably not going to know. And you're probably, honestly, not going to be able to figure it out either. I'm going to have to tell you the answer to this one. The displacement on a velocity time graph is quite a bit harder to find than the displacement on a position time graph. Position time is up and over, subtract the 2. On a velocity time graph, what we have to do is find the area between the line and the x-axis. So we would, in this case, there's no way that I could find the area of that shape directly, so I have to break it up into a triangle and say the area of that triangle is 1/2 base times height, and the area of that rectangle is base times height, and then we add them together. So the displacement equals the area. Now, it gets a little bit more confusing even. If you happen to have a displacement that's underneath the x-axis like this, then we would make it negative. If we happen to have some that's above the x-axis and some that's below the x-axis, you have to add them all together, making sure that the ones that are below the x-axis are considered negative values. So up until we get to displacement, it's a little bit different than position time graphs, but not really any harder. Once we get to displacement, it's a little bit harder. We've never found that area before.